Hello, my name is Andrew Wysocki, and I'm here at the University of Michigan. And this summer, I worked under Professor David Wentzloff on designing an energy harvesting circuit that worked with the headphone jack on either like a PC or any kind of mobile device. And let me start off by describing what energy harvesting really is. So energy harvesting is a process by which energy is derived from external sources and then captured and then possibly stored for small electronic devices. And the reason I decided to go with attempting to harvest energy from the headphone jack is because it's pretty universal and it's really easy to connect and it's found on all kinds of devices. So some of the goals that we started with for this project was, first we needed to find a way to take the audio signal and convert it to something more useful like a DC power supply. And another goal on this besides just that is we had to make it pretty universal so it could be crossed between different devices, and also, since it's pretty low power, it needed to be very highly efficient. And since there was a little bit of deciding to do because audio channels are separated, it's not just one channel, so we actually had a decision to make whether or not to use two channels or just use one. So for this project, we decided to use one channel for power and then leave the other one open so that it can be used to send some kind of signal, possibly audio, since that's what it's designed for. And here at the bottom, I have a quick block diagram of how this whole AC to DC process works. So first, you can start with a transformer to either step up or step down the voltage, and then rectify it to make the signal completely positive, and then some kind of smoothing filter to make it pretty close to a DC like power supply. And then you can regulate it with a component that will allow you to adjust to a specific level, and it'll also make it a very constant source. So what I started with is characterizing the output of the PC, and I just stuck with a PC sound card to make it simple. And it's important to know that the output from this is AC coupled, which means you cannot send any kind of DC signal through there. So when trying to decide the sound wave to send through, you have to know it's got to be AC. And also it's important to know what kind of load is usually associated with this so you don't mess up anything and make sure everything works right. So usually it's about a 15 to 60 ohm load, so we had to kind of stay in that range. And also we knew that the audio frequency output from this is 20 hertz to 20 kilohertz, so that can be pretty limiting on the design process. And also it was measured experimentally that the output voltage was 3.04 volts, and that can help decide what kind of components to choose. So everyone likes things simplified, so sound cards can be pretty complicated. So it's always easy to get some kind of equivalent circuit that will allow you to build your circuit and attach it to it. So the way I went about doing this is to use some kind of frequency response, and that usually is pretty direct on getting what the circuit is. So after sweeping through a whole bunch of frequencies from the output of the audio port, I got a voltage supply of 3 volts, which is what we measured. And then we found an internal resistance of about 1.2 ohms, internal capacitance of about 220 microfarads. And also on here I have the R test, that's just the load we applied to find the frequency, to find the output. And also, based on this simplified circuit, we found that the frequency needs to be at least 1 kilohertz or higher, or else the signal will start to get attenuated too much, and you won't really get much transfer. So speaking of power transfer, this is what we did to fully characterize what kind of power we could get from it. And this plot that we have up on here is it's a IV characteristic plot, which shows the current and voltage related to each other. And that's the blue curve right there. And next to it is the red curve, which is the power transfer. And you can easily see there's a defined maximum power there. And that's shown at about 68 milliamps and 970 millivolts. And that concludes to about 15 ohms, which if you noticed, that 15 ohm maximum power isn't equivalent to the 1.2 ohm resistor that we calculated from the frequency response. So there's something going on here which can be attributed to the current limiting, which you can see as a straight line across. And next here this is the actual circuit design itself, now that I had all the characterizations done. And we had about 7 stages in the circuit. The first one was the transformer that I talked about before. And this was a step-up transformer since we're dealing with such low voltages. And then from there, we had a synchronous MOSFET bridge, which this allowed for a really high efficient rectification, whereas using diodes, which is typically what's used, would cause a lot of energy loss. And since I'm not using diodes in the bridge, there needed to be some kind of current blocking diode, because the MOSFETs will easily accept current back into them, and you want to make sure that the current is unidirectional. And from there, I added a regulator, which allowed me to adjust the current and the voltage to what I wanted. And it was a low dropout one, so it's good for low power, and it is pretty high efficient. And next, I had a voltage divider, which allowed me for the next part is the application of what I used. And I actually used some 3-band audio equalizer, and from there I had a summing amplifier. And this was all pretty low power, so it worked well with the circuit, and it allowed for the right channel, which I mentioned previously before, that left channel was power and the right channel was there for some kind of signal. So this allows me to combine the two. So the left one powers these equalizers, and the right one sends an audio signal through them, such as music or something, so you can listen to it. So the voltage divider is set before that, which allows the power supply to be right in the middle between the high and low rails on the power supply, or on the amplifiers. So, and then I can skip ahead here. So this is the schematic that we have, and these are labeled the components that we have there. So 1 is the transformer, and 2 is the FET rectification, and 3 is the blocking diode, 4 is the regulator, 5 is the voltage divider, 6 are the 3 different bands for the equalizer, and then 7 is the summing amplifier. And right after the summing amplifier is the output, which you could then send to like a headphone or something. So that concludes my presentation, and overall this summer I learned quite a bit, and I am glad that I got to spend the time with Professor David Wentzloff. Thanks.